So today's webinar is going to cover a portion of the fluid storage handling application and conditioning, conditioning being a fancy word for describing filtration. So the second half we will definitely discuss filtration of lubricants and what that all entails. So to begin, I always like to start with some definitions or at least some statistics to help us understand why we're so concerned about this. This is a fairly old study that was done, and one of the things I like about this study was the first definition. When Dr. Rabinowitz put together this data, he described the failures as not using the word failure. He described it using the word loss of usefulness. His implication was that a failure isn't necessarily when something stops working altogether or when something blows up and rips itself to pieces. He was describing is that it simply doesn't perform in the way it was intended to perform. So a loss of efficiency, a trip that is immediately reset, anything like that still qualifies in his book as a loss of usefulness and not simply just grouped under the term failure. So when he put together this study, you can see that the biggest slice of the first column is surface deterioration, which is just a fancy way of saying essentially wear. But when he described wear in the next column over, he broke it into two categories, and the predominant slices were corrosion and what he did call wear. So in the standard terms now, we typically refer to these as chemical and physical, corrosion being a chemical wear mechanism, and what he's described as wear being a physical wear mechanism. Once we break down the physical wear categories, you can see that the predominant players have something to do with particulate, whether it's adhesive wear, metal-to-metal contact, creating wear particles, or if it's abrasive wear, meaning the particles are perhaps being generated externally and causing some of the wear, and that would be three-body abrasion, or if the particles are being generated simply by the two bodies together, so that's your two-body wear. The long and the short of it is that if you look at a study like this, it shows that the largest single source of wear leading to a loss of usefulness is going to be particle-induced. Now, a different study that was done only a few years later, and this one is fairly widely cited. It's quite a common one to refer to because it looked at different industries across an entire nation, and the nation that was chosen was Canada, simply because I'm sure it was a small enough pool that it was easier to collect the data. But they showed how wear and friction had losses in industry, and they broke it out according to industry. Once they did that, they also looked at what types of wear would be the main contributors. And as you can see from this one, abrasion, which again goes to our two and three body wear, accounts for the largest slice of the pie, and adhesion is another major slice. What you also can include, though, is erosion. Erosion, kind of like sandblasting, and that particles floating around in the oil as they make a sudden turn or flow through an orifice, they may cause some further wear. So if you add up those three slices of the pie, you'll find that that accounts for about 82% of the wear. So particles are of primary concern. That's the whole point of these two different studies, that most of the wear, whether you want to say it is more than 50% or you just want to say it's the single largest slice of the pie, most of the wear that we're looking at in terms of lubricated components is going to be attributed to some sort of particle contamination. So that's why we're so concerned about storage, handling, even the application of the lubricants, and then of course the conditioning, the filtration of the lubricants after they've been put into play. So one quick definition to get out of the way, because I will use it frequently, is the word micron. Micron is the same as a micrometer. It's simply 1/1,000,000th of a meter. When we talk about microns, if you want to think of it in imperial units, it's 0.04 thou of an inch. Easy way of looking at it is, generally speaking, the smallest particle the human eye can detect is somewhere around 40 microns or just under. That's what normal dust particles fall into that category. They're just big enough to be visible. Human hair, as you can see, is about twice that. It's about 80 microns across. So when I start talking about microns and I'm using values far less than 80 and even less than 40, you'll know we're talking about some very, very small particulate, but on the other hand, you're going to see how significant some of that stuff is. So one other study I'd like to show you, and again, anytime you see studies, I always encourage people to take these with a grain of salt, or at least try and understand what they're telling you and who's telling you this. Because as we always joke, big tobacco will release studies telling you that smoking is not harmful. So if somebody's got an agenda when they release a study, it tends to be biased or might have a slant to it. So this study was published by SKF. So this is a bearing supplier who's giving us this information. But what they're showing us is what is the bearing life in comparison to filtration. So starting on the far right at 40 microns filtration, they're suggesting that we could get maybe 3 million cycles on a particular bearing they used in the study. If we zip way over to the left and look at filtration at 10 microns, we can just about double that and we'll get close to 5 million cycles. If we go to 5 microns filtration, it jumps up to 8 million cycles, and if we can get all the way down to 1 micron filtration, we'll see nearly 13 million cycles. So what they're encouraging you to see within this study is that changing your filtration from 40 microns to 1 micron would yield a nearly 4 times life extension. But one of the things I always say about looking at studies is there's 3 words I try and keep in mind when I view any of this type of information. And those 3 words are practical, feasible, and economical. Is it practical to move from 40 micron to 1 micron? Well, there will be some logistics involved in that because a 1 micron filter will have to be sized completely differently than a 40 micron filter due to backflow pressures and overall flow rate through the filter. Is it feasible? Do I even have the real estate to be able to accomplish this? And economical. If I got a 4 times life extension on the bearing, would that be cost beneficial compared to what I had to spend upgrading the filtration system? And if I can't say that something's practical, feasible, and economical, I'm probably not going to recommend going ahead with it. So when I look at this study, where I like to draw your attention to is somewhere around the 5 micron filtration. At 5 micron filtration, we can probably get that done practically. It's usually quite feasible, and the economics work out much better then. So that would be about a 3 times life extension. Worst case scenario, a 2 times life extension. Point being, yes, we can see where in that curve meets reality. Where the curve starts to get very theoretical is in the far, far left. So one of the things to consider about this study is looking at some other information that exists out there is what is the most damaging size particle? Well, one paper suggests that that's between 2 and 22 microns in size, and another paper published quite a few years before it says that the 1 to 5 micron range is what's the most damaging size particle. Well, in effect, they're both saying exactly the same thing, even though the numbers look kind of different. Their whole point is the most damaging size of particle happens to be clearance sized. Clearance-sized particles are just big enough to contact both surfaces in relative motion. If it's smaller than clearance, it'll go through without contacting either surface, and if it's larger than clearance, it can't get in there to do any of the damage. So clearance-sized particles are the most damaging. So the comment about 2 to 22 and 1 to 5 are actually both saying the same thing. And if we look at a chart of some typical clearances, you can see that the 1 to 5 micron range covers a significant portion of the typical clearances in most lubricated equipment. 2 to 22 is simply a little broader. So we can see that particles are our biggest enemy in a lubricant, and the particles that we're concerned with are the ones we can't see, not with the naked eye anyways. So let's have a quick discussion then about where do they come from. We know that we have this particulate. It's been documented as in terms of its size. It's been documented in terms of its damage. But where did it come from in the first place? What kind of particulate might it be? Well, basically, you're going to find essentially 3 broad categories that you could classify the particulate as having its source be external, or it may be internal, but it was generated internally, or it was built in, another form of internal, but was there right from manufacture. So taking a deeper look into the external sources, understand that your environment plays a key role in how much contamination gets into a lubricated piece of equipment. Some pieces of equipment breathe more than others, and if they do so, they will definitely breathe in more particulate. But we also have, and why I put it first, is sometimes this is the overlooked side, some that are process related. What's the lubricated asset doing, and is it coming into contact with whatever we're trying to make it do? So compressors are a great example. As they compress air, the dust that may be in the air, and certainly the moisture that's in the air, can enter into the lubricant. Now, if we start compressing something other than air, we may now be compressing some form of chemical, and that chemical may have some negative reaction with it and may not be as clean as air. Not to say air is that clean, but some processes are far dirtier than just compressing air for instrument air or plant air. When we have other processes that are purposely creating particulate, like crushers and mills, well, then you're going to generate a lot more dust, and it's quite possible that some of that may enter past a seal into the lubricant, and it'll certainly enter the environment, and we'll see it come in through the breathers. Pumps are yet another good example of where you might find the process entering the lubricant, because with a pump, there's often just a very small seal between whatever it's pumping and a lubricated bearing. If that seal even remotely begins to fail, you will get some of the process into the lubricant, and we can have some very adverse effects. But going over to the other side, like I said, we do commonly think of dust in the atmosphere breathing into the system as a source of contamination, but we need to look at every other point of entry. So if there's any kind of seal between the lubricant and the outside, whether it is a seal on a shaft that's rotating, or simply a flat seal on a tank lid or a hatch, all those are points of entry. Wherever we fill the oil into the system, that fill cap or plug, that's a potential source. And certainly any inspection covers or any other sight glasses and whatnot that cause a breach in the overall reservoir or piping so that you can see the lubricant, all of these have the ability to contribute contamination. And it's simply that they may not be sealed correctly, they may not be adequate, they may have damage to them. Many times we've seen spikes in particle counts on systems that have been running fine for years, and all it turns out is somebody didn't replace a dipstick or didn't put a fill cap on properly, or perhaps even a breather was damaged. But looking towards the internal sources, when we start looking at the potential for creating particles, we get much longer lists. So when we talk about the surfaces in relative motion to each other, we have many different wear mechanisms that can kick into play, and all of these will produce additional particulate. So running down the list real quick, abrasive wear is when you have two surfaces coming into contact with each other. One surface rubs, the other one loses. Basically, this is like sandpaper on wood. Adhesive wear, one of the other terms for adhesive wear that makes it far easier to understand is called scuffing. Scuffing is when there is a sliding contact, and instead of being, say, one rough surface against a smoother surface, it can be two smooth surfaces that normally wouldn't cause any abrasive wear, but they're coming under such high pressure contact that essentially what happens is one smears on the other one. There may even be temporary welding of materials, and then as they pull apart, particulate becomes or gets generated. Cavitation wear is exactly what you think of as in terms of cavitation. If you have microbubbles being imploded near a metal surface, it will of course cause damage to the metal surface, and when those particles of the metal surface are released, they become a contaminant. Corrosive wear is just simply stating rust and oxidation reactions. They create soft oxide layers on the metal. As that oxide layer wears off or is rubbed off, it will generate a lot of particulate. Erosive wear is the sandblasting. So as particulate that already is in the system floats around and impinges on other metal surfaces, it will generate more metallic wear. Fatigue wear is something that occurs in rotating equipment, whether it be pitch line to pitch line contact in gear teeth, or if it's the rolling element bearings. you will see that over time, this stress that is placed on the metal parts will cause subsurface cracks. When those cracks do propagate to the surface, spalls are formed. Those spalls become contaminants. Some of the other hardware that we use as part of our lubrication system has the ability to contribute particulate. Certainly any hoses that we have may, as they wear or degrade over time, release small rubber or whatever other materials are made with particles, as well as the fibers that are holding it all together. Filters, though they're designed to remove things from oil, they sometimes are contributing if they, again, begin to fail. Paints and coatings don't often wear, as they're not typically used in high turbulence areas, but they can degrade over time, particularly if we don't have a suitable lubricant in there. If we've got something incompatible, you will dissolve or otherwise alter the coating that may be protecting the metals, and as the paint wears off, it becomes a contaminant. Last but not least are seals. Seals are designed to keep stuff out, but seals are in contact with moving parts. And sometimes the seals may wear, and they will generate some form of contamination. But more what I'm getting at is sometimes a seal is holding another contaminant against the moving part. It's designed to keep it out, but it doesn't mean it keeps it from contacting. So you can see some pretty significant seal wear in rotating applications, and it's not that the seal did the damage, it's that the seal held some sort of rough particulate against the rotating shaft, as an example. Now within the fluid itself can generate some contaminants. One of the easy ones to come across is additive dropout. If we do get higher water content in oils, sometimes the additives will react with the water. The water, of course, wants to settle out at the bottom. If it does that, it becomes kind of like a contaminant because now it's concentrated and not necessarily in the area we want it to work in. If we see rapid darkening of fluid, often this is attributed to carbon particles. Carbon particles can be produced through a number of ways. Oxidation is sort of the go-to answer, but I'd rather point out two other ones. Electrostatic spark discharge or microdieseling are both mechanisms that generate black particles very quickly, very aggressively, and they're of the size that can be quite damaging. When we do talk about oxidation, we don't necessarily think of soot particles alone. We tend to call it something a bit slimier or goopier, like sludge, varnish, tars, lacquers, things like this. If the oxidation goes to an extreme temperature, we tend to refer to that stuff as coke. It is a black, much harder looking deposit. And last but not least, when it comes to fluids and contaminants, we simply call it incompatible mixtures. It could just be two different oils that don't play well together. It could be oil and process. It doesn't matter, but in some cases, we have them appearing as a contaminant that displaces the lubricant layer. Other times they may react with the lubricant and produce other things like gels or otherwise sludges that take on anything from the consistency of Vaseline to peanut butter, in that range there, where it really starts to stick to things. It can plug up filters, plug up suction intakes, cause all kinds of problems. But these are all forms of contamination that occur internally due to sometimes normal mechanisms, but oftentimes accelerated by something abnormal happening within the system. Last but not least, we know that some particulate is there before we even put the lubricant in. Sometimes the contamination is there because we try to do something good to the system. So that's why I start the first column with service. Anytime something is being serviced, if it's being opened up, it's being exposed, or at least given the potential to get further contaminated. So when we think about some of the activities that we do, are we doing these activities in a way that tries to prevent the system from becoming contaminated? I know a lot of people employ FME, which at least prevents people from leaving rags and wrenches behind, but did they keep things covered up in a way that prevented normal airborne dust and contaminants? Because again, just to stress it one more time, the particles that cause the most damage are the ones we can't see. The stuff you can see typically is not a big deal. Further down the service column, anytime we do an inspection, something as simple as pulling a dipstick out to confirm a level, opening a hatch to look for foaming, things like this will allow the opportunity for contaminants to get in. And then definitely top-ups. New oil is not clean oil. You're going to learn more about that throughout this particular webinar. And anytime we add oil, what if we're using dirty components? A dirty pail, a dirty funnel. Sometimes you'll see that people have hydraulic hoses, but they let them dangle on the ground or otherwise get contaminated. So when they connect the fittings together, they're in fact pushing contamination into the oil. In the other column, from the manufacturing side, from the assembly of the equipment in the first place, we will often find high levels of contamination. Starting at the top of that list, there's a quick story about Corvette. Corvette had a major issue with premature engine wear, which upon oil analysis was attributed to silica sand. So they started tracing this backwards and realized that many of their cars had high levels of silica sand. So after checking a bunch of cars at the dealerships, they started checking cars coming off the assembly lines, and even then it still had high levels of silicon. So they started looking at the oil fill from the factory, which did not have silicon. So they said sometime after the car gets oil, but before it rolls off the assembly line, it's picking up all this silicon. Well, that actually wasn't the truth. What they did find in the end, after some very thorough investigation, was that if you know anything about Corvettes, one of the things that Corvette has prided itself on is its low weight. And to accomplish a low weight, it's made from a fiberglass shell, but was one of the first vehicles to mass produce an aluminum block engine. So the aluminum block engines, the way they're created is by sand casting. And as it turned out, some of the engine blocks were not being thoroughly cleaned as they were being assembled. So there was actually leftover foundry sand inside the engine. And it didn't do anything until they filled it with a lubricant, and the lubricant was able to circulate it to some of the other moving parts. And at that point, it caused the premature wear. Carrying down our list, anytime you apply new piping to a system, if it's being cut or threaded or whatnot, you're going to create a lot of metal shavings. Those metal shavings can be quite damaging in the system. And again, I'm not referring to the ones you can see. I'm referring to all the little tiny bits that are also created that you tend to ignore because you can't see them or don't see them as easily. When we weld anything, oftentimes when we weld, we're welding from the outside only. We're not doing anything on the inside, so we're not noticing any of this little spatters that are created. And this can also generate particulate that many of these spatters can be quite small and even damaging. When we go through rebuilds or do some of the commissioning, we may use sandblasting or bead blasting. When we do this, the beads that we're using or the sand that we're using is not necessarily that damaging because it tends to be quite large, but as it removes material, whether it be oxides, lacquers, paints, whatever it's doing, if we don't fully flush all those out, the remaining particles can be quite damaging. Second last on the list is preservation materials. I'm not actually referring to anything solid there. I'm referring to preservation oil. There's been many of our customers who have had issues over the years with a brand new piece of equipment that's not been properly flushed. Once it's filled with the final lube, there tends to be some issues, and nothing seems to be wrong with the lube, but there does seem to be a reaction going on. And what we in the end can usually attribute it to is a reaction to the original preservation oil that wasn't flushed out. They simply topped it up with some residual preservation fluid in there. There's often some compatibilities between that preservation fluid and fully formulated products. Last but not least, sometimes when we do these rebuilds or turnarounds, we'll go in, we'll clean things up, we'll use a variety of chemicals. We may use rags, we may use different solvents. Generally, in and of themselves, they're not necessarily harmful, but when we leave them behind or leave portions of them behind, because one of the things I always like to joke about lint-free rags is a lint-free rag is only lint-free if you don't rub it on anything. As soon as you rub it, it will generate fibers. Those fibers can be damaging. In the bare minimum, they can prematurely plug up a filter. But the chemicals and solvents we use, sometimes they cause negative reactions with the final fill lubricant if they're not properly flushed or neutralized. So as you can see, we've got a long list of potential contaminants. Generally, many of them have a form of particulate behind them or will at least generate a form of particulate. So that's where we're going to start with our concern is what can we do about all this? So where the presentation really begins is here. In the fluid storage, handling, and conditioning section, basically we can break this down into 5 steps. And we can't cover all 5 steps today. We're going to have to cover 2 or 3 of them and leave the other ones for the next webinar. But the 5 steps basically lay out like this. Step number 1 is simply admitting new oil is not clean oil. If we can come to grips with that, we can start taking some corrective actions to make sure that we're going to, in the bare minimum, not allow the lubricant to get any dirtier, but maybe see what we can do to make it cleaner. Once we've accepted delivery of a lubricant, we now need to store it. When we store it, we need to look at the ways that we can help, again, prevent it from getting any dirtier and possibly clean it up a little bit. Once we actually need the lubricant and we're pulling it out of storage, we must once again start looking at those tools and say, are they being used in a way that's going to prevent it from getting any dirtier? And perhaps we can again make it one step cleaner. By the time it's into the lubricated component, now we talk about exclusion. What are we doing that is keeping it from getting any dirtier? And then step number 5 is conditioning. What are we doing that perhaps is going to help clean it up? So starting with step number 1, this is a pretty easy step. New oil is simply not clean. You can't say it any other way. One of the reasons it's not clean is look at this standard. If you're familiar with ANSI AGMA 9005, this is a standard for industrial lubrication. And within it, there's a section on acceptability for new oil cleanliness. And you see the direct quote here. It says it simply must be free of visible, suspended, or settled contaminants at the time it is installed for use. So basically, if you pull a sample, hold the bottle up to the light, and you don't see anything in it, that's considered clean. Well, like I said earlier, the human eye sees particles down to about 40 microns, maybe a little less, depending on your eyesight. These aren't the size particles we're concerned with. It's the stuff that's way smaller than that. So this standard is terrible. It's not that helpful to us, but it is the go-to standard for fluid cleanliness. Now, in terms of equipment, we have API standard 614. This standard talks about the commissioning of new equipment, and it is not very good either. So one of the things that you'll read about it is it suggests doing a 1-hour oil flush. Now, the time is the same regardless of the size of the system, so right away you should already see a flaw in this logic. The next part of the flaw is the flush is done at only the design flow rate. Well, if you know anything about flushing, the faster you can get the velocity of the oil, the better it will be at actually cleaning things. If you just flow the oil nice and slow, you're not really going to get anywhere near the effect. The third thing, though, is that it says this 1-hour flush at design flow rate needs to employ 100 mesh screens. Well, the little note I put at the bottom there tells you that a 100 mesh is equivalent to about a 159 micron filter. So these screens are not really removing the stuff that we should be most concerned about. But then keep reading. Read the quote here. This is directly from API 614, and it says to further verify the cleanliness, the system shall be inspected at 2 to 6 points. So again, it's not being terribly specific here. You can have 2 screens, you can have up to 6 screens, doesn't matter. And then it says selected by the inspector in terms of where you put them. So you don't necessarily have to put them after the components. You can put them before the major components. So essentially you're checking piping rather than checking something that's critical. The quote continues, the system shall be considered clean when foreign matter such as, and it gives a bunch of examples, are not visible to the eye and grittiness is not detectable to the touch. So if you cannot see them on a 159 micron screen and you can't feel them with your fingers, you've properly commissioned that piece of equipment and it has now been certified as clean according to API 614. So hopefully between those 2 standards, you're noticing that there's a definite flaw in industry in supporting getting clean oil and having the piece of equipment cleaned during any commissioning or turnarounds. We're not working with very good standards, so if we're not working with a good standard, it's only going to be logical that down the road we're going to see this contributing to some of our problems. So continuing with step 1, when we can accept that new oil is not clean oil, we need to then set a target for how clean should it be. So the little number I'm giving you here is a typical, and I'm just saying based on our experience, this is not, no one's held to this number, but the typical cleanliness that we see of new oils, and this is regardless of delivery, could be tote, could be drum, could be bulk, doesn't really seem to make much difference. But that comes out to an ISO code of about 2019-16. And what I'm suggesting to you is that 2019-16 is about 8 times dirtier than would be typical of an OEM recommendation. Now, where I'm getting this is that 2019-16, as you can see on the left there, is at least 3 codes higher than what would be recommended in an OEM. Now, the picture on the right, that happens to be a hydraulic OEM cleanliness, and that, as you can see, is approximately 6 codes lower. Well, if you know anything about ISO codes, every time we move by 1 ISO code, it's a 2-fold increase in particle count. So to go from a 14 to a 20, to go from 14 to 15 is twice as many. 15 to 16 is now twice again, so 4 times. 16 to 17 is twice again, so 8 times. And you can see how this just compounds itself. So I'm suggesting to you that the upper limit for many OEMs is at least 3 codes lower than what we see as a typical new oil cleanliness. And what we can sometimes see in more sensitive systems is more than 3 codes. We can see 4, 5, 6 codes lower. So that is pretty significant in terms of how dirty new oil is compared to how clean the system would like to see it. Now, since I'm talking about ISO codes, let's all get on the same page on that one, because I know some people don't understand ISO codes, or at least it's a bit of a mystery to them. So when we talk about ISO codes and we give 3 numbers, what we're actually referring to is 3 size ranges that we have for particulate. So the 3 size ranges in order are greater than 4, greater than 6, and greater than 14 microns. These are all how many particles were counted in that range per milliliter of fluid. Now, 1 milliliter of fluid is a cubic centimeters worth of fluid. If you go, how big is a cubic centimeter? Basically, it's the size of the tip of your pinky. It's not a very large volume of fluid at all. And we're counting hundreds or thousands or sometimes even hundreds of thousands of particles in that 1 single milliliter. Now, one of the things to note about these ranges is that they're not 4 to 6 and 6 to 14. They're everything greater than 4, everything greater than 6, and everything greater than 14. So what this means is that if I count a particle as being larger than 14 microns, I will count it again as being larger than 6 microns, and I will count it again as being larger than 4 microns. So when we talk about particle counts, it therefore should be no mystery as to why the greater than 4 micron particle count is always the highest number. The 6 is the next highest, and the 14 is the lowest of the 3. But it's because they're counting the same particles over and over and over again, just basically broadening the range a little bit. So when we report an ISO code, we are reporting them in that order, 4, 6, and 14, and we're coding them. So people then say, well, what's the code? How do I rationalize the code in my head? Well, ISO has created the coding system, which you can see in the left-hand columns here. Now, the left-hand column on the left side of the slide is the actual ISO code. The 2 columns to the right of it are identifying the lower and upper end of the ranges. So start at the 5th line from the bottom, an ISO code of 10. If you notice, an ISO code of 10 has between 5 and 10 particles per milliliter. If you move up 1 line to an ISO code of 11, it has now doubled to 10 and 20. If you go up 1 more to 12, you see that it doubled again to 20 to 40. So these are the ranges. This is the pattern. Every time we go up 1 code, we are doubling the number of particles at the lower and the upper end. So it's entirely a doubling effect. So like I said, if we go up 3 codes, we're 2 times 2 times 2 higher, so we're 8 times higher. If we're 6 codes higher, well, now we're 128 times higher. So what ISO has done is they created these ISO codes to assign themselves to these ranges. So what you do is you take your particle count, which if we look at the top right table, you take your actual count, so your 4 micron is 151,773 particles per milliliter at that size, and we find out what code it matches up with. Well, that's somewhere between 80,000 and 160,000, which is ISO code of 24, so we assign it the number 24. 6 micron, as you can see then, it gets assigned to 22. The 14 micron ends up being assigned 19. So that upper particle count, instead of looking at the actual count, you would simply refer to that broadly as a 24, 22, 19. So if you're following along so far, hopefully what you've seen is we've taken one set of numbers which we did not understand, and we simply turned it into a second set of numbers which we still don't really understand, but they're at least smaller numbers. So keeping this ISO code range in mind, just take a look at this example here. We have got 3 samples in a row, which if you look from the first to the second to the third sample, we definitely see some increases here. And they look fairly substantial, right? They nearly double. But if we start with the first sample and we start coding the results, we will start to see just what the codes do and how they help us understand particle counts. So starting with the 4 micron value on the first sample, 1,357 particles per milliliter. Well, the range according to ISO is 1,300 to 2,500 is an ISO code of 18. So the first number we'd fill in is 18. 361, an ISO code of 16, has a range of 320 to 640. So that number turns out to be 16. And an ISO code of 14, at 14 microns of 42 particles per mil. An ISO code of 13 is between 40 and 80 particles per milliliter. So that first sample would end up being rated as an 18, 16, 13. Well, if we keep running down the line here and code the second and third sample, what you would actually find out, given those ranges I just rattled off, all 3 of those samples end up being 18, 16, 13s. And this is what ISO is doing. ISO is trying to take away some of the resolution of the test and just broadly put the answers in the same ballpark. So we can see that all 3 samples are in fact 18, 16, 13. So according to ISO, these are all roughly the same cleanliness. There's not an appreciable enough difference between those results to think of them at all differently. So hopefully I'm making a little bit more sense out of particle counts right now, but you probably still have one lingering question. And that question that at least I find is quite common is, well, how much is that? If I have 18, 16, 13, is that like a pound of dirt per drum, or how much is this? Help me quantify what 18, 16, 13 would look like. Well, thankfully we have Caterpillar, who did a little experiment, and they can provide a visual on this one. 18, 16, 13 was what they found was the particle count that could be generated if you took a drum of oil, 55 gallons, and contaminated it with a half a teaspoon worth of material. So taking an oil that had been already filtered to have nothing in it, it only took 1/2 teaspoon of essentially dust and dirt to bring it all the way up to 18, 16, 13. So considering 18, 16, 13, we know that that's 1/2 teaspoon approximately. If I was to go up 2 codes, so I were to go to a 20, 18, 15, which is pretty close to what I said was a typical new oil cleanliness, you would see that that'd be twice as much and twice as much again of particulate. So 2 times 1/2 teaspoon is 1 teaspoon, and times 2 again is 2 teaspoons. So the joke that could be made is that a 20, 18, 16 drum of oil is going to have approximately 2 teaspoons of dirt. So you can borrow the slogan from Kellogg's Raisin Bran, and there's essentially 2 teaspoons of dirt in every drum of oil, minimum. But like I said, new oil cleanliness is typically somewhere around a 20, 19, 16, which is 2, if not 3 codes higher than that. So you should expect between 2 and 4 teaspoons worth of dirt in every drum of oil. And this is regardless of distributor, regardless of manufacturer, regardless of shipping container. It doesn't matter if it's plastic, steel, or whatever. But 2019, 16, just to put it into perspective, if we compare that to used engine oil, used engine oil at the end of drain, this is when you should be changing your oil, will be significantly contaminated, and I think we can all appreciate that. Most of us who've seen used engine oil know that it's quite black. It sometimes even feels a little gritty. If you do a particle count on used engine oil, you're going to find values of approximately 23, 22, 19, which, as you can see, is exactly 3 codes higher in each category, meaning it is doubled, doubled, and doubled one more time higher in dirt content. So that's 8 times dirtier. But imagine this. Imagine you have a hydraulic system and you introduce brand new oil straight from the drum into the hydraulic system. You're essentially doing a step change that's almost twice as bad as that. So 2019-16, our new oil on the left, compared to the upper limit of a hydraulic system, which is somewhere around 16, 15, 12, which turns out is 4 codes lower, it means that the hydraulic system wants to see an oil being delivered to it that is approximately 16 times cleaner than new. And that is as its upper limit. That's not even its target. That's its limit. So new oil is not clean oil, and merely introducing new oil to a system is sometimes all the contamination it takes to put an oil analysis report into alarm. So this is why it's so heavily stressed in many industries to pre-filter our oils, whether we pre-filter them as we take delivery of them, when certain storage, as we dispense them, or to at least at the minimum expect that the particle counts will increase after an oil has been put into a system before the system gets a chance to circulate it and clean it back up. So hopefully ISO codes are making a bit more sense to you now. You have an idea as to how to read the codes relative one to the next, but also a visual on what that might look like in terms of how much dirt, at least per drum. So getting back to step 1, we need to understand new oil is not clean oil. Now, we talked about setting a target cleanliness level, but again, let me stress this to you. There's the difference between a target and a limit, and that is often about 2 ISO codes variance from each other. The target is what you are hoping to hit. The limit is what number, if you hit, you would have to do a corrective action. So we typically separate those by 2 ISO codes just to make sure that we're not always in alarm. So this is how you set a target. This is the lower of the 2 numbers. So this is not the oil analysis limit on a report that we're going for. This is not the number that we would be trying to decide a corrective action on. This is what we're aiming to hit. So this chart is produced by HiPro. I like HiPro's take on it, not because the numbers are any better than somebody else's chart, but because they contain extra columns of information. The extra columns refer to what filtration would be required to even remotely come close to hitting the target. So if you go through this exercise and you pick your target cleanliness and then you look to the column to the right of it and you see the filtration that's required and you realize that you are nowhere near that level of filtration, you know you're probably not going to hit your target. So at least this helps balance, again, practical, feasible, and economical, and keeps you grounded in reality. So how you use this chart is you don't set ISO target cleanlinesses based on the type of asset that it's coming out of. You don't blindly apply the same limit for all gearboxes or all pumps or all compressors. What you look at is what are the moving parts, the lubricated parts within the system. So to give you a quick example, imagine we have some sort of hydraulic system and it's got a variable piston pump, it's got a servo valve, and it's got a journal bearing in it. So those are at least 3 types of components we have within our system. This system operates at over 3,000 psi. So what we do is we look at each of those 3 components within these tables, and whatever value is the lowest value for all 3 of those components becomes the target for the entire system. So starting with the top table, variable piston pump is the second line from the bottom. Look way over to the right at 3,000 psi or higher, and you see the target cleanliness should be 16, 14, 12. So keep that number in the back of your head for a minute or two. If we go to the lower table, we can find the servo valve that we had in our system, and it's the very bottom line. Again, look way to the right for over 3,000 psi, and that target says it should be 15, 13, 10. Well, 15, 13, 10 is lower, cleaner than 16, 14, 12, so we can ignore 16, 14, 12. We don't need to remember that number anymore. 15, 13, 10 is what's required to properly protect the servo valve. If we can target that number, it will more than protect the variable piston pump. Now, I also said it had a journal bearing, which is continued on the next slide here. If you look at journal bearing, that is found in the top table, and it doesn't matter if it's high speed or low speed, and pressure doesn't seem to be a difference. We have a target of 17, 15, 12, which is higher than the 15, 13, 10 that we're already discussing, so this number is not relevant. 15, 13, 10 was the lowest of the three numbers. That is the target for the entire system. And that's how you go about using these tables. Right? It's not based on the type of machine it's coming out of, it's based on the components within the machine and the operating pressure. So I quite like this table. It's I find quite useful. It gets me my answers, and if I was to just quickly go back to the servo valve at 15, 13, 10 in the bottom right there, you'd see I need at least a 5 micron beta 1000 filter, or I might need a 3 micron beta 200 filter. So if I know my filtration is somewhere within that range, I can probably hit my target of 15, 13, 10. But if I have an OEM 25 micron filter, I should not expect that I'm going to even remotely come close to this target. So make sure you set your targets realistically based on the other factors within your system. So that's step one. New oil is not clean oil, but let's set a target for what we need to hit. Step two, once we received it, we need to store it. How do we store a lubricant so that it doesn't get any dirtier than how we received it? And are there any things we can do to clean it up? So within step two, we always need to look at how we store it and where we store it. Ideally, it'd be nice to store everything inside. That helps prevent a fair amount of contamination. But we do need to look at how we store it within that area. So the picture on the left shows nice, clean drums. Things are looking happy. The drum on the right, on the other hand, shows that we probably have some breathing going through that bunghole because we're probably getting the moisture from the atmosphere condensing, or rain or snow on that drum. We see a lot of rust and oxidation. So this is not a good thing because it means that there's water outside a bunghole that is breathing, so we're probably breathing in at least the water, but we're generating a ton of rust, so we could be breathing in rust particles. So it's very possible that drum on the right can show a high level of wear metals when it actually hasn't even gone through a system that should be wearing. Now, if you do have to store drums outside in particular, you want to pay close attention to how you store them to try and prevent moisture from building up on the tops of the drums. Ideally, you'd store the drums horizontally. If they're stored horizontally, the common goal to aim for is to make sure that the bungs are below the fluid level. So the easiest way to do that is to put them at the 9 and the 3 o'clock positions. That way you've got lubricant pressed up against the bungs. The drum can't breathe outside contamination into the drum anymore. If you do have to store them vertically, it's recommended that they be completely covered. If they can't be completely covered, then at least tip them so that the water will accumulate somewhere away from the bunghole. So again, you typically tip them so that the 9 and the 3 o'clock positions are horizontal to the tipping. The idea is that if it's going to breathe, try and have it breathe only air, not breathe any rain, snow, or other liquids. When you have your drums in play and they've been opened and you are dispensing from them from your storage area, always make sure you put your caps and bungs back on. Leaving drums open to the atmosphere, even just for the sake of saying that, well, you need to let the drum breathe in air as you dispense fluid, that's going to introduce contamination. So we should employ some good housekeeping practices. We want to keep the system that the oil is going into as clean as possible, so therefore we need to treat the oil that we're storing in as respectful as a manner as possible. So we're going to keep everything clean, everything buttoned up tight. Here's an example of a fairly well laid out area. This is not a dedicated lube room. It's not a separate building just for lubes. They were basically working with the space as best as they could. But what they did was they arranged the drums according to oil type, and they used first in, first out inventory. So the oldest drums are furthest back. They're the ones closest to the wall. On the walls, they installed rack-mounted filtration, which has 2 levels of filtration. So you could install a coarse and a fine filter. You could install a particulate and a water filter, whatever you want. But the drum that's closest to the wall can be hooked up in kidney lube to circulate the oil through the drum. And it takes maybe an hour and a half, 2 hours to filter an entire drum of oil. But they would pre-filter the oil so that the drum that was in play, the one that was open, had oil that was already meeting the ISO target for the systems. Now, because you've got the rack-mounted filtration there, it has a pump, because that's what's circulating the oil through the filters. Well, that pump is what you can also use to then suck from the drums and fill your oil fill containers, whether they be pails or oil safe containers or whatever it is. So a lot is being accomplished by a fairly simple setup, but you will notice that there are several rack-mounted filters because there's one for every type of oil. And that way it prevents cross-contamination between products. Now, some notes about storage is if you're just storing drums as an example, we should try and prevent the drum from being open. So it's always good to put the bungs back in. If you want to leave it open, well then leave it open and protect it with a breather. Now, as you need to open up the other bung to be able to dispense from the drum, it's always good to, again, replace that bung when you're done. But if you want a more ergonomic type solution, it's good to, instead of having people always trying to remove and replace a bung plug, why not install a quick connect? With a quick connect, it doesn't require tools. It stays sealed as soon as you break the connection. Lots of things are good. So the example that I'm showing you here is just one of many, but this allows for horizontal or vertical storage of the drums. It provides a breather protection for the air going in and quick connects for filling and dispensing from that drum. You notice there are two quick connects, so this does allow for kidney loop filtration while the oil is in storage. So you can pre-filter the oils while they sit. You can filter the oils as they come out. Just to wrap up one more step here, and I think we'll hit our natural break point, or as close as we can get to a natural break point. Step 3, what happens once we need the lubricant out of storage? We need to take it to the asset. Well, again, I always try and stress this point that if you're going to move a lubricant, try and move it through a filter. So always consider using a filter cart or other filtration devices to help you move that lubricant from storage and into the asset. Another note is when you're using very small volumes and maybe a filter cart doesn't make sense to try and fill something with, use decent quality transfer containers, not open top metal jugs, repurposed plastic containers, things like this. Jugs that are designed to hold oil, keep it contained, keep it clean. Now, when we talk about filtering the oil from storage, here's just a couple other examples. This one is a plastic tote design. It's fairly lightweight. It's easy to manipulate by hand when it's empty, but you'll notice it has onboard filtration and breathers on it. So this allows you to filter the oil as you fill the tanks in the first place. When you take it into storage, it allows you to kidney loop it while it sits there, and of course allows you one more level of filtration as you dispense from them. So it's great. Slightly higher quality design. These ones are metal containers. They kind of stack like Lego blocks. The more you stack them, the greater the volume you have. But again, they have onboard filtration. They have onboard breathers. Because they're dual stage filtration, you can put coarse and fine particulate filters, or you can put a particulate in a water removal filter, and you can make your oils clean and dry. If you're dealing with smaller volumes, there's still ways of doing this. I'd like to point out that even something as simple as a barrel pump can have a filter on it. And it doesn't have to be a powered barrel pump like you see here. It could still be a hand-actuated barrel pump. But you can install filtration on the outlet of the pump. And these are as simple as buying automotive filter manifolds from a local parts distributor like Pep Boys or O'Reilly's or whatever you've got in your area. But if you buy these filter manifolds and install them on the output of your barrel pumps, I encourage you to buy twice as many filters as you require. If you install the filters on the outlet of the pump, an automotive filter is not a great filter, but one pass of filtration is better than no passes. The reason I say buy twice as many filters as you need is if you take the extra filters and thread a little 2 or 3 inch nipple into the bottom of the filter, you turn it upside down, it'll thread right into the small bung hole on that drum, and it becomes your breather, and a very inexpensive breather at that. If you're not pumping directly from a drum, you can use pumps like this one. Basically, they're portable. They have duplex or triplex filtration on them. You can set them on the ground. You can set them on a drum. You can set them on a tote. They can be electrically powered or air powered, and they'll kick the lubricant through the filters, whether, again, like I said, duplex or triplex, and provide you with at least one pass worth of filtration as you dispense your lubricants. With regards to the small transfer containers, some of the key criteria that you're looking for is that, well, they should be sealed, right? They shouldn't allow further contamination to get into them. It's nice if they have spouts on them to make pouring a bit easier. Some don't have spouts. They actually have hoses on them, like you see the yellow one there. I do encourage them to be at least somewhat transparent, just as a visual identifier that the oil color looks right, that you're not adding in something radically different. And preferentially, they should be color-coded. Color coding is very useful to help prevent mixing of wrong products. I do encourage that you not only use a color, but you also use the shape. So you'd use, like Lucky Charms here, you might have a green moon with a yellow star and a red horseshoe or whatever it's going to be. But using shapes and colors together helps prevent those mix-ups. It should be noted that most of these oil-safe type containers, they do have color-coded lids, but they also have color-coded collars on the bottle. So that's what allows you to get more combinations than simply the 5 colors that they typically offer. You can now add in 5 other colors of collars, so basically you've expanded your number of lubricant choices up to about 25. Now, when we talk about these containers, one of the major flaws most people point out about transfer containers, like the ones previously pictured, was the only way to fill them is to remove a giant cap. You can upgrade them. This is a different manufacturer that makes similar containers. It has everything we just talked about: spouts, transparency, sealing, etc. But it also has quick connects, so those can be filled directly from filter carts and filter pumps without having to open up the top. So there's definitely a wide range of products that exist out there. They do help prevent further contamination and help encourage additional filtration along the way. Now, the ones I've just shown you are all related to oil, so I should say a little word about greases here. But when we have greases, we can color code and have transparency as well. Obviously, the cartridges the grease comes in are not transparent, but that's the part we want to see. We don't need to see the grease itself. We just want to confirm the cartridge is the correct cartridge, and you can buy these. First place I ever saw them was from Lubrication Engineering. They had their own version. They were quite nice. Just to point out, you don't have to buy the whole grease gun over again. You can buy just the cartridge body. They only thread for the normal size cartridges. I haven't seen them for the oversized ones. But the neat thing is that they are color-coded, so you can color code where you're putting your grease in. You can always read the cartridge name, so you know you've got the right cartridge in the grease gun. And if you're looking for one other source to buy these from, cleargreaseguns.com is yet another retailer, so that's at least an easy enough website to remember. Just to wrap up the color coding though, like I said, colors and shapes together are very useful. It helps read them in low light conditions, and there's a fair number of the population that are to some degree colorblind, so you don't want people mixing up, say, a blue with a purple if you can't tell the difference between them even under good lighting. So adding a shape just helps give you a wider variety of selections and ensures that you've got a good visual confirmation that you are putting the right lubricant in, not just the clean lubricant. There's no point being clean if you've got the wrong one in there. So that concludes the first webinar. We'll stop here and we'll rejoin the second part, not next week, but the week after.